Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is Taylor Series. As always, please be attentive while watching this video. Taylor series is called Taylor because it was named after a mathematician. Brooke Taylor was an English mathematician who added to mathematics a whole new branch now called calculus of finite differences. He invented integration by parts and discovered the celebrated formula known as Taylor's expansion. Taylor and Maclairan was a Scottish mathematician who published his first systematic exposition of Newton's method, written as a reply to Berkeley's attack on the calculus for its lack of rigorous foundations. Maclairan series is often a term used to denote the Taylor series about x equals 0. In the past, from working in the Learning Commons and teaching this course, I've learned that students get really confused. They don't realize that these are really the same thing. So I will tend not to use the phrase Maclairan series, but we will do Taylor series about x equal to 0. By way of introduction, in the previous section we started looking at writing down a power series representation of a function. The problem with the approach in that section, that previous lecture, is that everything came down to needing to be able to relate the function in some way to 1 over 1 minus x. And while there are many functions out there that can be related to this function, there are many more that can't be related to this, so a more general approach is of interest. So without taking anything away from the process that we looked at in the previous lecture, what we need to do is come up with a more general method for writing a power series representation for a given function. So, for the time being, we're going to make two assumptions. First, we will assume that the function f of x does in fact have a power series representation about x equal a. This is kind of a bold assumption. It will be justified later, but this is a bold assumption. And so we'll say that f of x does equal to the summation from n equaling 0 to infinity of c sub n times x minus a to the nth power. And so that's c0 plus c1 times x minus a plus c2 times x minus a whole squared plus c3 times x minus a whole cubed plus c4 times x minus a whole to the fourth plus dot dot dot. The second assumption is we're going to assume that the function f of x has derivatives of every order and that we can in fact find them all. This is perhaps an equally bold assumption. Now that we've assumed that this exists, we need to figure out what are these c sub n's. And this is easier than you might have thought it to be. First, we're just going to evaluate everything at x equal a. Well, when you put x equal a in there, all the terms drop out except the very first term. And so f of a is equal to c0. Because all of those other terms with the x minus a's drop out. So all the terms except the first are 0, and we know that c0 is f at a. Unfortunately, there isn't any other value of x that we can plug into the function that will allow us to quickly find any other coefficients. However, if we take the derivative of the function and its power series term by term, and then plug in x to the a, we get, so when you take the derivative, the constant term drops out, and the derivative of x minus a to the first power is 1. So you're getting f prime of x is going to be c1 plus, and then this was x minus a whole squared, so you get the 2 c2 x minus a. This was cubed. This is 3 c3 x minus a whole squared. This was x to the fourth, or x minus a whole to the fourth, so that's going to be 4 c4 x minus a cubed plus dot dot dot. And now when we substitute f prime of a in, all of these terms drop out and you're left with f prime of a is c1. So now we know c1. Now we continue taking the next derivative, which means c1 drops out. The derivative of this becomes 2. Now this is the second derivative of f with respect to x, becomes 2c2, plus, this is now 3 times 2. You should check these calculations. C3 times x minus a, 4 times 3, C4 x minus 2 whole squared plus dot dot dot. So what we can do is we can substitute x equal a again, and so f double prime at a is equal to 2c2. So when we solve, we get c2 is f double prime at a over 2. The third derivative becomes this, and when we put a in, all these terms drop out, and we find that f triple prime, the third derivative evaluated at a, is 6 times c3, so that c3 is f triple prime at a 3 times 2. The fourth derivative gives you this, and when you put x equal a, this drops out, and so the fourth derivative evaluated at a is going to be, and this is going to be 22, but it's instructive to look at this as 4 times 3 times 2, c4. So c4 is equal to the fourth derivative, and we've started using this notation rather than putting a whole bunch of apostrophes that we have to count. If we put it in parentheses, that means the fourth derivative evaluated at a divided by, and this is 4 times 3 times 2. Now you're starting to recognize a pattern here, and in general, we have the following formula for the coefficients. C sub n, the nth coefficient, is equal to the nth derivative of f evaluated at a divided by, and this is n factorial. And this even works for n equals 0 because 0 factorial is 1. And so the zeroth derivative is just the function itself. So provided a power series representation for the function f about the point x equal a exists, the Taylor series for f of x about x equal a is this. F of x is equal to the summation n equal 0 to infinity, and this is f raised to the, this is the nth derivative evaluated at a over n factorial times x minus a whole to the n. And here it is written out explicitly in a expanded form for you to see. Now if we use a equals 0, we're talking about the Taylor series about 0, and people call this Maclairan series for f of x. And here's that, and you notice that we're really just plugging in 0 for a. And so you see these are going to be x minus 0. This is x minus 0 whole squared. This is x minus 0 whole cubed, and so on and so forth. This is simpler, but this, please do not make this a big deal. It is simply the Taylor series evaluated at about the point x equal to, or a rather, is equal to 0. Now before we work in examples of Taylor series, we have to address the assumption that a Taylor series will in fact exist for a given function. And so what we're really doing is we're talking about doing the partial sum. So this is t sub n, which is also called the nth degree Taylor polynomial for f. This is t sub n. So you see t sub n is a sequence that converges to the full Taylor series as n goes to infinity. But this is nothing more than a polynomial of degree at most n. And so what we're really talking about is these polynomials will converge to the Taylor series, so that nth degree Taylor polynomials for f will converge down here, and this is the just the partial sum for the series. So now we're starting to get on kind of familiar ground. And then we can talk about the remainder. Well, the remainder is how different is this polynomial from f of x, and that is called r sub n, and that's the remainder. And this is really just the error between the function f of x and the nth degree polynomial. And so f of x is equal to tn plus rn, and here's the theorem about does f of x really be represented by its Taylor polynomial. And suppose that f of x is equal to this, where t sub n and R sub n are as defined above. Then if the limit of the remainder, the error, goes to 0 as n goes to infinity, for the absolute value of x minus a less than r, that's the radius of convergence, and the interval of convergence is from it is the interval associated with the absolute value of x minus a less than r. It is the interval centered at a. Sometimes people will talk about the Taylor series centered at a. Then f of x, in fact, does equal its Taylor expansion within that interval. Now, in general, showing that that limit goes to 0 is somewhat difficult, and we will revisit that later in this lecture. But for now, we're just assuming that this can be done in all of the examples that we're going to be looking at. It's, again, a bold assumption, but we're going to get good at the calculation. So example 1, and again, this is a good thing for you to work on now and when you study for the final exam. Find the Taylor series for f of x equal e to the x about the point x equal to 0. Well, what we need to do is calculate all these derivatives. So every derivative that we take of e to the x, we always get e to the x back. And since we're expanding about x equal to 0, we're going to be substituting 0 in here, and e to the 0 is always 1. But remember that the denominator is always going to be the nth derivative evaluated at the point, in this case 0, so we get these coefficients. We're always dividing by n factorial, and then this is x minus 0 whole to the n. So you see e to the x is represented by, at least from this calculation, we haven't proven that this is the case, but when you look at the radius of convergence of this, you can say, oh yes, this is going to converge from minus infinity to positive infinity because this n factorial grows so quickly. So the representation of e to the x as a Taylor series is a summation from n equals 0 to infinity of x to the n divided by n factorial, a result that you want to commit to memory. Let's find out what is the Taylor series for f of x equal e to the minus x, again about x equals 0. And again, you should work this. Now there are two ways to do this problem. Both are fairly simple, but one of them requires quite a bit of work. It's simple work, but it's quite a bit of work. So we're going to show you both solutions. The longer one has some nice ideas that we'll see, and the other one illustrates a very important part. So what we're going to do is we're going to calculate what are the coefficients associated with this. So we're going to be taking the nth derivative evaluated at 0 for f of x equaling e to the minus x. So we're taking those derivatives. But when we're taking the derivatives, we have the chain rule. So these are going to alternate being 1 minus 1, 1 minus 1. And down here, the nth derivative is going to be minus 1 to the nth e to the minus x. And that means this is minus 1 to the nth power because e to the 0 is 0. So you see we've got a pattern happening. And so what we're going to do is we can write then that e to the minus x is equal to the summation n equals 0 to infinity. This is minus 1 whole to the n, x to the n over n factorial. It indeed is an alternating series. Now that previous solution wasn't too bad, but in this case there's a much shorter solution. You see earlier we figured out what was e to the x about 0 for really any value of x. So what we can do is we can plug in minus x into the formula we have for e to the x. So e to the x is the summation n equal 0 to infinity, and we just put what x is here, but this time we're putting minus x in instead, and it turns out that the power series, because it is like a polynomial, still works. So here we can just substitute. We get minus x whole to the n over n factorial, and then minus 1 to the nth power is this, and you see we get the same answer. We got it much quicker this way, and this is something you want to add to your toolkit. Let's continue to add to our toolkit. Here we're to find the Taylor series for f of x equal x to the fourth, and this is e to the minus 3x squared about x equals 0. And again, this is a problem that you should become very familiar with. Now, instead of taking the derivative of this product and using chain rules and everything else, which we could do, and we will get the answer, we're going to do something that builds upon our prior work. For example, we know that e to the minus x squared, e to the minus 3x squared is like e to the z. And the power series for e to the z about 0 is going to be the summation n equal 0 to infinity z to the n over n factorial. But now z is going to be 3x squared. Actually, it is minus 3x squared. So I just put minus 3x squared into the power series, raise it to the n, and I have this. And this is going to be minus 3 to the n times x. Now this is x to the 2n over n factorial. Now I have this x to the fourth out here, but we also learned, because power series are like polynomials, I can distribute that x to the fourth in there. So x to the fourth is added here, and so not added, multiplied, and so that gives us the addition of exponents. So the final answer for this, x to the fourth e to the minus 3x squared, is the summation from n equals 0 to infinity minus 3 whole to the n. This is x to the 2n plus 4, all divided by n factorial. Pretty powerful stuff, huh? Let's expand something about a different point. So this time we're going to say, find the Taylor series for f of x equal e to the minus x about the point x equal minus 4. So now we're expanding it about a different point. So you see what we're going to have here is, and you might say, oh, it's going to be the same coefficients. No, it's not, because the coefficients depend on this point. So we need to find a general formula for the nth derivative at minus 4. And what you find, and you should verify this for yourself, that f, the nth derivative, is going to be minus 1 to the n, e to the minus n. But when you plug in minus 4, you're going to get e to the 4. A minus times a minus is a plus. And so this is what you get for the numerator of the coefficients. So the Taylor series then is e to the minus x expanded about x equal minus 4 is the summation n equal 0 to infinity. This is minus 1 to the n, e to the fourth over n factorial, and this is x minus minus, or x plus 4 whole to the n. Make sure you understand this example. So you see, expanding at a different point is a totally different answer, and usually what you're doing is you're expanding this about a point that you're particularly interested in, and that means these terms start getting small. That means that this power series converges not only because of the n factorial, but because this number is small, it converges very fast, and this allows for great engineering approximations. All right, let's do something that does not involve the exponential function. Let's find the Taylor series for f of x is equal to cosine of x. And by the way, cosine of x is infinitely differentiable because you can take the derivative forever and you never get 0. And we're expanding this about x equals 0. So first we are going to be calculating our coefficients again. So the first derivative isn't a derivative at all, and I'm expanding it about 0, so I get 1. But then the first derivative is minus sine, I get 0. The next derivative is minus cosine, I get minus 1, 0, 1, 0, minus 1, and dot, dot, dot. Now what that means is that only when the derivative is even do we get a 1. When it's odd, we get 0, and these alternate in signs, S-I-G-N-S. So this is positive, negative, positive, negative. So cosine of x then is equal to the summation from n equals 0 to infinity, the nth derivative evaluated at 0, that's what we were doing up here, all over n factorial times x to the n. But you see, we're getting 0 except where these are even. And so we can write the series for the cosine of x the following way. The cosine of x is a summation from n equals 0 to infinity. We're only picking up the even terms. So we're going to be alternating signs. So this is going to be minus 1 to the nth power. But this is only the even value. So this is x to the 2n. And this is 2n whole factorial. Now we reordered these things, but this is a series that we need, and we'll often refer to this, and you want to commit this series to memory. And you might remember that, the cosine of x was what we called an even function, and it only has the even powers. Kind of impressive, actually. Let's do another problem. I forgot to put the little signal here, but I think you should know that by now. Find the Taylor series for f of x equals sine of x, about x equal to 0. So we start out with our calculations. Now there's some similarities and there's some differences. This time, and you might remember the sine of x is an odd function, and this time the odd derivatives are the even derivatives are 0, but the odd derivatives are not. And so when we take the derivatives, we will get 0, 1, 0, minus 1. So it's only the odd numbers that will happen, and the SIGNs will alternate. It will be plus 1, minus 1, plus 1, and minus 1, and so on and so forth. So it's a similar pattern, but it's actually very different. Because here you're only going to get the summation from n equals 0 to infinity f, the nth derivative evaluated as 0 over n factorial, and this is x minus 0 to the nth power. So when we write that, we get this as my expansion, only the odd exponents. So we see the Taylor expansion for the sine of x is, the sine of x is equal to the summation from 0 to infinity minus 1 to the n, and this is just the odd number, so this is x to the 2n plus 1 all over 2n plus 1 whole factorial. Again, another formula to be committed to memory. And let's do another Taylor series. Let's take the Taylor series for f of x equal the natural logarithm of x, but this time let's expand it about x equal 2. So we'll take the derivatives, and what you'll see is that the ln of x is ln of x, the derivative is 1 over x, the derivative of that is minus 1 over x squared, and this is 2 over x cubed, and then we start getting a little bit of a factorial thing going on. This is minus 2 times 3 over x to the 4th, and so on and so forth. Now, the general form here is going to be, so you see the fifth derivative is going to be 4 factorial, the fourth derivative is 3 factorial, the third derivative is 2 factorial, and in general the nth derivative is going to be n minus 1 factorial times minus 1 to the n plus 1 over x to the n. And I'm evaluating all of these at 2, so I put 2 in, and these are the numbers that I get. So my coefficients then in the Taylor series for the natural logarithm of x, and again we're expanding this about the point 2, is going to be the summation. We're valuing those derivatives at 2, and we plug them in, and what we're going to get is n factorial, and we get a 2 to the n because you notice we're getting 2 to the n when we plug in the 2's. So this natural logarithm then is, this is the natural logarithm of 2, that's f of 2, plus, and the rest of them, these do fall into this form. The summation now, this is n equal 1 to infinity, minus 1 whole to the n plus 1. This is n minus 1 factorial. This is n factorial 2 to the n, and it is times x minus 2 whole to the n. Let's do another example. Let's find the Taylor series for f of x equal 1 over x squared, but this time it's about x equal minus 1. Again, we take the derivatives and we observe a pattern. And then we substitute minus 1 in to get the coefficients of the numerator. And you notice that these are going to be, and there is a pattern that's emerging. This is the second derivative is going to be 2 factorial. The third derivative is going to be 4 factorial. The nth derivative is going to be n plus 1 factorial. And so the Taylor series is 1 over x squared is a summation. This is going to be n plus 1 factorial. That's what we got for the numerator divided by n factorial. And then this is x. This is minus a minus 1. That's x plus 1 whole to the n. And you see the factorial, n plus 1 factorial over n factorial is just going to give you n plus 1 n. So this is the summation from n equals 0 to infinity of, that is n plus 1 times x plus 1 whole to the nth power. Now we're going to work an example here where we have a polynomial. So suppose we have a third degree polynomial and we're going to expand it about x equal 3. Now by the time I get to the fourth derivative and beyond, this is going to be 0 already. So this is not going to be an infinite series. It will be finite. Here I take the derivatives, I evaluate them all at 3, and I will get these numbers. That means my solution is going to look like this. So this is equal to the summation from n equals 0 to infinity. This is the nth derivative evaluated 3 over n factorial. This is x minus 3 whole to the n. So I substitute all those numbers, and this is what I get. Now this is the same as this, but this is the Taylor series. And again, I'm going to emphasize that you want to memorize these important Taylor series for the e to the x, cosine of x, and sine of x. Now I'm going to say a couple more things about approximation using, and I'm going to just call this Taylor series polynomial. So suppose we wanted to use the fourth order Taylor polynomial to approximate the natural logarithm of 1.1. Well, we're going to let g of x, the function that we're using here, is going to be the ln of 1 plus x. So we will compute the Taylor coefficients, evaluate it at 0, because you see we're using 0.1, which is close to that, and we only go down to 4. So that means this is what we get for my expansion. Again, we're expanding about x equal to 0. We get this number. And so we can plug that in, and we get a very good approximation for what this logarithm is just by using a truncated Taylor series. And that's what they do in your science courses and your engineering courses and so on and so forth. Incredibly so. And in fact, what you find is near the point about which you expand something, the fit of the curve is really great. This is the 6th degree polynomial, and you see how it hugs the cosine curve when we're close to 0. Similarly, when we're close to this point here, the graph of this is the third polynomial for sine x, you can see that it really hugs the function. So these really do approximate very well if you're near the point about which you're expanding. It gets worse the further you get away. It gets worse the further you get away. And it gets better the more terms you have in your Taylor expansion. Here we're approximating the sine of x, and here we're approximating the cosine of x. You can see that it gets better and better the higher n is, and also the closer that you are to the point about which you expand. One final word about the remainder of a Taylor polynomial. We actually do have a form for this, and I really should mention this, and this is called the Lagrange form of the remainder. I'm not going to talk about the proof. It's really pretty involved. It involves the mean value theorem. But the remainder, you see, so if you stop with n terms, these are your n terms, but here's your remainder as we talked about. R sub n at x can be calculated to be the n plus first derivative evaluated at point z. Now z is a point between 0 and between x and c was what you were expanding this about. So this is the n plus first derivative at z divided by n plus 1 whole factorial x minus c to the n plus 1. Now having this representation means that we can bound the error, how wrong you can be, by the max of that n plus first derivative. We've actually talked about this kind of thing before when we were talking about the numerical integration, and then you get x minus c whole to the n plus 1 all over n plus 1 factorial. So this allows you to estimate how wrong you can be using the Lagrange form of the remainder. And here's an example where we're using the third Taylor polynomial for sine of x, and we're approximating how wrong can we be by stopping there. Well, you see, here's what we get for this, and there's R3 because we just go up to n equal 3. So this is the fourth derivative evaluated at z over 4 factorial, and this is x to the fourth. But we know that this remainder, R3, is equal to, for some value, the sine z over 4 factorial times the difference here, which is 0.1 raised to the fourth power. But the sine is bounded by 1 in absolute value, so you get this estimate, and that implies that the error term is really quite small. So we can ask questions about how big does n have to be, but you see very quickly you get a very useful approximation. And again, this is what they do in your engineering courses, your economics courses, and in your physics courses over and over and over again. And here we're approximating, we want the error for this logarithm of 1.2 to be less than this. So we need to figure out what n needs to be. So we calculate using the Lagrange formula, and we know that the derivative of the ln is less than, and that's really just going to be 0.02 in this estimate, and you get this. And in this interval, it is from 1 to 1.2, and so this is going to be, we're solving this basically 0.2 to the n plus 1 over n plus 1 has to be less than 0.001. And so we can find out what n has to be, and you only need n to be 3. So you see, often you don't need very many terms of the Taylor expansion. What your instructors are doing in your economics and engineering courses and physics courses actually is quite sound mathematically. Now there's a whole bunch of Taylor series that you can derive, and we derived actually many of these in our discussion. We didn't do the arcsine. You should actually do that, and the arctangent. And this is a special one, which is known as the Binomial Theorem. It's an infinite series, and we will talk about this specifically, and it is part of our syllabus. But another reason that we talk about it is that Isaac Newton actually was responsible for developing that and many other things. He was a great English mathematician, and they closed Cambridge down, where he was going to school, because of a disease. and he worked at home, and instead of just studying his math, he thought deeply about things and came up with that binomial theorem for fractional exponents, among other things. So there are COVID-19 analogies in Newton's life, and we will study that binomial theorem in a subsequent lecture. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. God bless you all.